Hello, here we have two problems related to mappings. So let's begin. The first problem, we have a space of continuous real functions, and we have a mapping phi that goes as follows. I have to prove that the image of phi consists of continuously differentiable functions, and that the kernel of phi is 0. Well, then we have to show that phi is injective but not bijective. So let's begin with showing that the image of phi consists of continuously differentiable functions. Suppose a function in the image is not continuously differentiable. So let's call that function u of t. Well, again, it's defined as integral from 0 to t f of s ds. And well, thing is, you can differentiate this function. And you will get f of t. So we have not even a contradiction, we could just go ahead and say that. We could say that we have some arbitrary value of the function, phi, and that, well, we can simply differentiate it and get f of t, which is said to be a continuous function. So the image is indeed continuously differentiable functions. Now we have to show that the kernel of phi is 0. So need to show when 0 from 0 to t f of s ds is supposed to be the 0 function. So for every value of t it's supposed to be 0. Well, for that to be true, let's go ahead and differentiate both sides. We have f of t equals 0. So f of t is for sure equal to 0. Now that would mean that definite integral from 0 to t of f of s ds is, well, bounded by 0, that's for one, that you can show easily. Another thing you can show is you can just go ahead and integrate 0. Well, you can show a bunch of stuff, but yeah, essentially this thing is 0 implies that f of t is equal to 0. So that's the only real valued continuous function that will satisfy this. So phi is indeed injective. Okay, wait, no, we're not told that phi is a linear mapping, so we still have to show that it's injective nevertheless. So we have showed that the kernel of phi is 0, now we have to show that phi is injective. Suppose that phi of x equals phi of f of x equals phi of g of x. Next we can do is we can get the value of the function. Okay, let's go differently. Let's pick the argument as t for consistency's sake. From 0 to t, f of s ds equals from 0 to t g of s ds. Now, if we were to differentiate both sides, we get f of t equals g of t. So that means that if phi of f of t equals phi of g of t, it implies that the functions are equal. So it is indeed injective. Now, to show that it's not bijective, we just need to show that if we were to take some function and then it's not going to be in the image despite being in the domain. So we have continuous functions. The image is continuously differentiable function, so we can take any function that is continuous but not differentiable. For example, f of t equals the absolute value of t. And now there is no such value of f of t that would map to this function, despite it being part of the codomain. So it's definitely not bijective. Okay, good. We have shown that. Let's continue. I have to prove that if phi from E to F and psi from E to G are linear mappings, then the relation kernel of phi is a subset of kernel of psi is necessary for the existence of linear mapping he from F to G such that psi is equal to he composition with phi. Okay, so what we have here is phi from E to F and psi from E to G and he from F to G. So let's make a tiny diagram. So from E to F, from F to G, and then we also have psi, which is composition of he and phi. Now he goes here, and phi goes here, so psi is supposed to be a composition. Now we have to show that this is for sure true if this is true. In other words, it's supposed to be necessary. Okay, let's go ahead. Let's try to compute the kernel of, well, the composition he and phi, which is also technically psi, whatever you want to call it. Okay, now thing is, this kernel has a nice property. Notice how he is a linear mapping. That means that 0 belongs to the kernel of he. Now, the kernel of this composition is essentially going to be every element x belongs to E such that phi of x belongs to the kernel of he. Now let's rewrite it in set builder notation. Phi of x belongs to the kernel of he, and x belongs to E. Okay, so that is the kernel of psi. Now, as for the kernel of phi, let's write it down. Let's know that it is the kernel of psi. Kernel of phi equals, now it's going to be phi of x equals 0 and x belongs to E. Now, thing is, you can notice these two things, and they're really similar. You know why they're similar? Because 0 belongs to kernel of E, so this set is entirely included in this set, because phi of 0 equals 0, and that belongs to kernel of E. In other words, we can rewrite this as essentially this set union with, well, let's copy paste this and have to include an extra condition. X does not equal to 0. Okay, no. We first have to specify where it belongs because, well, we're working with abstract algebra, different vectors, spaces, and stuff like that, so we do not exactly specify the space before saying which one of the zeros this is. So, not equal to the 0 of this space. Okay, good. Now, well, we can see that now that the kernel of phi is clearly a subset of kernel of psi. So we can write down that kernel of phi is a subset of kernel of psi. And now we can safely say that this arrangement implies this statement. That's it for today. Thank you for watching. Bye.